Hello everyone, I hope you all had a good weekend and are staying healthy. This week and next week we will be discussing raster data and analysis. This week I will largely focus on remote sensing and I'll go into further depth about the analysis portion next week. Before we discuss remote sensing, I want to quickly review the information about the raster data model that we went over a few weeks ago. Raster data models represent reality through grid cells in an image file. Each grid cell is given an attribute value. The cells are formed into rows and columns to represent the entirety of an area. Grid cells are usually square and evenly spaced, but do come in other shapes such as rectangles and hexagons. The model is continuous, but it can also represent discrete values. So when I say continuous here, I mean that there are no abrupt transitions like in the vector data model. Because of this, raster data is most often used for variables that change continuously across a region, like elevation. The cell coordinate is usually the center of the cell or centroid. That cell value is applied to the entire area that cell covers. If the entire area is uniform within that cell, then that cell is given that value. However, if it is not uniform, which is much more common, we have what is called within cell variation. If the values vary within the cell, the value is represented as the average, median, mode, minimum, or maximum value. There's also a big trade-off between spatial data detail and data size in raster datasets. A minimum of 4 cells are required to locate a feature or specific value, so the largest cell size you would want is 1/2 of the object that you are trying to locate. Having a smaller cell is advantageous because it gives you more detail, but it comes at a price. The number of cells needed to cover a given area increases 4 times when the cell size is cut in half. Smaller cells provide greater spatial detail, but it causes the dataset to increase significantly in size. That not only increases the amount of space it takes up on your computer, but also drastically increases the amount of time it takes to process. So what is remote sensing? Remote sensing is the procurement of information about an object or phenomenon without making direct physical contact with that object. This is different than in situ observations, which are on-site observations that can have a direct or close contact with that object. However, in order to most accurately interpret remotely sensed data, in situ data is often collected to calibrate the algorithm that helps us interpret the images. These images can be taken by a surveyor on an aircraft, such as planes and UAVs, as well as balloons, blimps, rockets, pigeons, kites, parachutes, and telescoping poles. Long before satellites and computers began to dominate the field, people had been taking pictures of the Earth's surface from afar. This was no easy task, and people risked their lives to further the development of the field. Remote sensing includes aerial photography, which is the earliest form of remote sensing, and I may use the terms interchangeably. For an overview this week, I will begin talking about the history of the camera, remote sensing, and then go into the electromagnetic spectrum. And then after that, we'll finally get into remote sensing, the what, how, then get into active and passive sensors, different data resolutions, the sensor bands, imagery types, and band uses.